Hello, my friends. Um, in this video, we are going to talk about uh, Thevenin and Norton analysis. Uh, by Thevenin's theorems, uh, if you are given a circuit, for instance, the circuit is a very complicated circuit, and you know there's a no terminal. The terminal at the output, say the terminal at the output is A and B. And this A and B is to be connected to a low resistor. We don't know even the low resistor. You just know we are going to analyze this circuit. So unknown circuit. By Thevenin's theorem, this circuit, this circuit can be translated into a much simpler one with a voltage source, and in series with an impedance. And I've shown that you have no knowledge of impedance. You only know resistance. In this case, I'm going to write resistance here. But in reality, right, we shouldn't do that. Uh, by Thevenin theorem, you are going to have an impedance, and this impedance is ZT. And this ZT is going to be connected in series with the voltage source. And this voltage source is called uh, Thevenin voltage. So almost every circuit, any circuit can be done in this way. It can be converted into Thevenin equivalence. And then the output here will be connected to an unknown. We don't know. So this is so-called Thevenin equivalent circuit. Any circuits can do the same thing. Any circuit can be converted in this way, in this manner. So this is Thevenin equivalent circuit. And Norton is even um, Norton have a similar one. And we have another Norton. By Norton theorem, you can convert any circuit into a so-called Norton equivalent circuit. And the Norton equivalent circuit is something like this. Uh, an impedance, and the impedance here is so-called Norton impedance. And in this case, the Norton equivalent circuit will contain the Norton impedance connected in parallel with the current source. And this current source is so-called Norton. Norton current source. And again, right, the terminal is A and B, which is exactly the same as this A and B here. The circuit characteristic will all be the same. And you can connect it to output A and B to the outside world. We don't care. We only care about this equivalent circuit today. So this is the basic of Thevenin's and Norton analysis. I'm going to illustrate to you uh, what is Thevenin and Norton conversion is. So before going on further, right, let's summarize the procedure of Norton analysis. The procedure is very simple. Tapping. So what is the procedure? Now, the step one is to open the output circuit. To open circuit the output. The second step, uh, let me check my notes, right? The second step is to find the voltage at the output terminal, and this voltage is going to be the so-called tapping voltage. Find the output voltage across the output terminal. And this voltage is called tapping voltage, VT. And the first step is to zero all the source, zero all the independent source. Independent source, right? It's important to emphasize this point. Independent source, all independent source. Independent sources. So if you have a voltage source, you zero it. This means you are going to stop it. So I better write this down, right? Short voltage source, short independent voltage source, and open circuit current, or the current source. And finally, um, we are going to determine uh, the output impedance. And this impedance is going to be uh, ZT. So the best thing I can do at this stage is to give you an example. It's very difficult, right? read the procedures here without any background. It's very difficult to interpret what is going on. So first of all, suppose we have a very simple circuit, and this so-called unknown circuit is the one here. You have a resistor P ohm, and then you have another resistor here, 6 ohm, and you have another resistor here, 7 ohm. And this circuit is connected to a voltage source, 12 volt. And I'm going to determine the um, and the output may be connected to something else, right? We don't know what the output is, the load is, the load is, right? We just know it is like this. So this is the example to illustrate the tapping procedure. The first step, find the voltage across the output terminal, and this is going to be the tapping voltage. So now, open circuit this first. First step, open circuit the output. So I remove the output, and then we are going to find this voltage. And this one is going to be the traffic voltage. According to what I can get here, um, there should be no voltage drop across this 7 ohm resistor. Uh, I will I will write this down. Right? The voltage across uh, this 6 ohm resistor is going to be 6, 12 times 6 divided by 3 plus 6. Uh, and this one is going to end you up with a voltage, and this voltage will be 8 volts. So I got it. The Thevenin voltage is 8 volts in this case. So step number 2 has been done. Step number 3, zero all the independent source. So now I want this voltage to be 0. So the best thing that you can do is to zero. And final step, uh, find the output impedance in this case. The output impedance in this case, right, is say the impedance is VT. Uh, it will be the 7 ohm times the parallel B in parallel with 6. In this case, um, by my mental calculation, this is going to be a resistance element, 9 ohm. So the equivalent circuit for this network is going to be a Thevenin source, which is A volts, and then connected in series with a 9 ohm resistor. And the point will remain the same. So this is the answer